Hi, this is Thomas. Welcome to math class. We're looking at differential calculus applications, and this application concept is the identification of the tangent line and the normal line for a given point on a particular function. First, let's look at a graph with the function y equals x squared. And we might want to know the tangent line at a particular point on the curve. So given the equation y equals x squared, any point on the curve is x squared. The y value equals x squared. The tangent line is going to be the slope of the curve, or have the slope of the curve at the particular point that we're analyzing. And the point we're analyzing is a point on the tangent line. So the calculation of the tangent line equation is based on identifying the point of tangency, as well as the slope of the tangent line, which is based on the derivative of the function. The derivative of the function will give us the slope of the function at a given x input. That's the slope calculation, and we use that slope and the point of tangency to calculate the line formula for the tangent line. The normal line is the perpendicular to the tangent line, and what we do to calculate the normal line is we calculate the opposite inverse or negative inverse of the slope of the tangent line. Using the derivative, we calculate the slope of the curve at the point we're analyzing, and that value, we take the negative inverse to be the slope of the normal, and then we use the point of tangency, which is also on the normal line, to calculate the line equation for the normal line. Let's evaluate the function y equals 9 over the square root of x for an x value of 9. First step is to calculate the point of contact. And this is a point on the original function. So to calculate the point of contact, I want to know the y value when x equals 9. So I'm going to calculate the function of 9 equals 9 divided by the square root of x is now the square root of 9, which is 9 divided by 3. 9 divided by 3 is 3. So my point of contact is 9 for the x value and 3 for the y value. Next, I'll calculate my derivative function, f prime of x. And it helps to rewrite the original function. So I'm going to rewrite the original function. Y equals 9 times x to the power of negative 1/2. Looking at the original function, we have the square root of x in the denominator. That is equivalent to x to the power of negative 1/2. And now when I calculate my derivative, I'll have my constant multiple 9 times, and I'll use the power rule, bring down my exponent, negative 1/2 times x, and I'll reduce my exponent by a value of 1. Negative 1/2 minus 1 is negative 3/2. So now I have my derivative function. And I can simplify to negative 9 over 2 x to the power of negative 3 over 2. Next, step 3, I'm going to calculate my slope, or my gradient. And the calculation of slope is based on my x input of 9. So I want to calculate the output for the derivative at a value of 9, and that will be the slope of the tangent line. So when I input 9 in place of x in the derivative equation, I have negative 9/2 times 9 to the power of negative 3/2. We can simplify to negative 9/2 times 1/27, which will simplify to negative 1/6. So the slope of our tangent line is negative 1/6, and one of the points on the tangent line is 9, 3. Now, so we can visualize that slope and compare it to a graph. I'll add in the graph of this function on the left side of the screen. This is going to be the graph of y equals 9 divided by the square root of x, which will be a downward sloping curve in the first quadrant. And we're looking at an x value of 9. And we can see that at that x value of 9, and of course this is a sketch, so this is an estimate, if I want to draw in a tangent line at that point, it's relatively flat and going up and to the left. Up and to the left means negative slope, relatively flat means a slope less than 1, and absolute value less than 1. And we see we have negative 1/6. The absolute value 1/6 is less than 1, and it's a negative slope, which is the direction that we've drawn into our graph. So the calculated slope is in line with the graphed slope of the tangent line. And I can also add in now my normal line, which will go through the same point and be perpendicular to the tangent. So when we calculate the normal line equation, we expect to have a steep positive slope looking at this normal line in the graph. So we have a visual confirm that our slope calculation of negative 1/6 is reasonable. Let's continue with the line equation. So when I have one point and a slope, I can calculate my line formula as y minus the y coordinate of my point, which is 3, equals my slope, negative 1/6, times x minus the x coordinate of the point, which is 9. And simplifying to the slope-intercept format or gradient-intercept format, I have y equals negative 1/6x, is negative 1/6 times x, plus 9/6, which is negative 1/6 times negative 9, plus 3. On the left-hand side of the equation, I had a negative 3. I'll add 3 to both sides to move that to the right side of the equation. And I can simplify to y equals negative 1/6x plus 9/2. 9/6 plus 3 equals 9/2. So now I have my line equation for the tangent line, and this was step 4, the line equation. And what we're doing in 3 and 4 is calculating the tangent line equation. Let's look at the adjustments for the normal line equation. First, I'm going to take the opposite inverse of my slope. So the slope of the tangent line, negative 1/6, will become positive 6/1. And I'm intersecting the same point, 9, 3. So I'll use the same x and y value. I'll simply use my negative inverted slope of 6/1. Y minus 3 equals 6 times x minus 9. and y equals 6x, and we can see there we have the steep positive slope we're expecting for the normal line, minus 54 plus 3, bringing the negative 3 over by adding 3 to both sides. And my final equation for the normal, y equals 6x minus 51. This concludes part 1 of tangents and normals. In part 2, we're going to look at an additional concept relating to calculating tangent line equations.